Hi, welcome back to General Chemistry 1. I'm Dr. Fang Xu. In this video, we're going to talk about exceptions to the Octet rules. Although Octet rule itself is very useful and probably covers majority of times when you write the correct Lewis structure, there are a few exceptions that we need to keep in mind. The first type is a deficient Octet rules. Deficient Octet rule means those four atoms with the atomic number 1 to 5, they can have less than 8 electrons, including shared electrons in the Lewis structure. So in this periodic table, the first 5 atoms are hydrogen, helium, lithium, beryllium, and boron. So for these 5 atoms, when it forms a stable Lewis structure, the electrons around it may be less than 8. So for example, here in the methane structure, hydrogen only has one single bond around it. So there are only 2 electrons around hydrogen, less than 8. In the Lewis structure of boron trichloride, in the boron, around boron, there are only 3 single bonds. So that is, there are 6 electrons around boron, also less than 8. But both of these Lewis structures are stable. A second type is expanded octet rules. Like you can tell by the name, the expanded octet rules are for atoms in the period 3 to 7. When they are the central atoms in a Lewis structure, the filled outer level of electrons can be more than 8. So these atoms are non-metals and from 3rd period and on. So 1 to 3. These elements are phosphorus, sulfur, chlorine, argon, selenium, bromine, krypton, iodine, xenon, and ATRN, those 2 lines. And there are 2 more in the 7th period. I did not include it here because of the limited space. So if you see any of these nonmetals, and they need to be the central atom in a Lewis structure, then it can have more than 8 electrons around it. For example, here, if we have phosphorus pentachloride, then we have 5 single bonds around phosphorus, and phosphorus is a central atom. So there are 10 electrons around this phosphorus. It follows the expanded octet rule. And also in the selenium trioxide, there are 6 bonds in total, so 3 double bonds. In total, we have 12 electrons around selenium. So that also is an example of the expanded octet rule. You need to know the possible situations and possible atoms that follow the deficient octet rule and expanded octet rule. The third scenario, molecules with odd electron atoms, this is just for a reference. Okay, so these are called free radicals. These are species whose Lewis structure contains a lone or unpaired electron. Just give you one example. Here, we have nitrogen dioxide. So when you see this Lewis structure, and obviously it's a resonance structure, there is one lone electron here in nitrogen, or it can have a one lone electron here in one of the oxygen, terminal oxygens. So these lone electrons are not quite commonly seen in Lewis structures, but when you see it, it's still possibly true, and it's the molecules is odd electron atoms, or it's called free radicals. Okay, so let's do a practice of drawing Lewis structures with this exceptions of octet rules. Please draw the most stable Lewis structure of sulfur hexafluoride. You may take out scratch sheet and pause the video and try to work it out yourself first. All right, let's try 2 different methods. Still, the method 1 is to distribute valence electrons. And first, we need to lay out the structure. There's only 1 sulfur and 6 fluorine. So sulfur will be put in the center, and fluorine will, put in the position surrounding the sulfur. So let's do that. We have 6 fluorines around sulfur, and now we need to count the total valence electrons. For sulfur, it's in the 6A group, so it's 6 valence electrons. Fluorine is in a 7A group. Each fluorine has 7 valence electrons. So in total, we have 48 electrons of 1 sulfur and 6 fluorine. Okay, then we start to form a single bond between sulfur and fluorine. In each sulfur and fluorine, so now we have 6 single bonds. That is 6 times 2, that equals to 12 electrons used. So the remaining valence electrons is 36. Okay, with that 36 valence electrons, we can start to fill in Joule-Lewis. We can Joule-Lewis structures from the surrounding atoms and make sure they follow the octet rule, and then we can take care of the central atom. So fluorine, it already have 1 bond, so it has 2 electrons. We need to put 6 electrons in 3 pairs around each fluorine. And we have 6 fluorines, so 6 times 6, that equals to 36. We can use up all of the valence electrons. Okay, so now we have the structure. Sulfur, because it's in the 3rd period of a non-metal, so it can have the structure, and it's the expanded octet rule. Let's finally check if the blue structure is stable by using the formal charge variation. For any of the fluorine here, the formal charge of the fluorine at 7, the original valence electrons, minus 6 dots here and minus 1 bond, that equals to 0. For sulfur, it has 6 valence electrons before, does not have any loose dots, but has 6 single bonds. So the formal charge for the central sulfur is also 0. So that kind of explained why sulfur breaks the octet rule, but this Lewis structure is still stable because it has the best formal charge you can ever imagine. All atoms here are 0, have a 0 formal charge. Okay, so if we use another method to write this Lewis structure, we can write Lewis structure from Lewis dot structures of atoms. So sulfur has 6 valence electrons around it. And then we have fluorine that has 7 valence electrons around it. If we want to pair up the lone electrons, there are only 2 electrons in sulfur can do the pair. So what we can do now is to break 2 pairs of lone electrons in sulfur as 4 single unpaired electrons. So now each of these unpaired electrons from sulfur can pair up with lone electron of fluorine, and we have 6 of them. So then we'll have the same structure as we come up with method 1, and also you need to do the formal charge variation and do that. So the trick for this method 2 is when you have bonds, but you don't have enough unpaired electrons or lone electrons, you can split a pair of electrons to 2 unpaired electrons to facilitate these bond formation. All right, this is the end of this video, and I'll see you next time.